Welcome to the Masters of Reliability webinar series, Optimizing Underground Cable Rehabilitation Options. My name is Chrissy, and I'll be your moderator for today's session. We encourage you to submit any questions that you may have into the chat, and we will address them at the end of the webinar. I will now hand it over to Wade Pfeiffer, Vice President of Sales and Marketing at Novinium, to introduce our guest speaker.
Thanks, Chrissy. Hello, everyone. Proud to say that we have Darren Johnson, President and Director of the Asset Management Practice at BIS Consulting here with us today. Darren's a mechanical engineer with over 20 years of experience working with many utilities across North America, helping them justify and optimize their rehabilitation options. His cable assessments have been used to get millions of dollars of funding for cable rehabilitation for many utilities. Darren, welcome. I'll now turn the presentation over to you.
Thanks, Wade, and thanks, everybody, for taking the time to be here. I hope you'll find this presentation to be interesting and informative. What you're looking at here is a list of utilities throughout North America and actually across the world who have used the economic life optimization methodology that we're going to be talking about today. We'll be discussing it specifically in the context of underground cable. And I show you this just to make the point that this technology or this approach is well proven and has been applied very broadly. It's not new ground that anybody would be breaking. So let's start at the very beginning and kind of frame up the problem that utilities with underground cable are facing. And this is very common, and that is that large amounts of cable were installed starting maybe in the late 1960s, and that the older vintages of that cable, especially the older style XLPE cable, is suspect. So many utilities are seeing the rate of faults increase over time, and there's a concern that this trend will continue and will affect reliability. The question is, given that that's the case, now what? What can be done about that, and what should be done about that? And that's where this cable evaluation approach that we're going to talk about comes into play. The purpose of asset management is to solve this problem that virtually every utility faces. This is the situation, that there's a lot of information and knowledge and experience at the level of maintenance and operators and engineers. They understand their system very well. They know how it's performing. And they probably have a very good idea what needs to be done to keep everything up on its feet. The trouble is that they have a hard time explaining the need for spending in a way that resonates with non-technical stakeholders. So there's kind of this tension between the pocket protector people on one hand and the green eye shades people on the other hand. And the purpose of asset management is to bridge this gap, to translate the technical understanding at one part of the organization into a cost-benefit analysis that speaks to non-technical stakeholders. And that's true of the cable evaluation process that we're going to be talking about next. We're talking about a process for evaluating a spending decision, and I want to make what I think is a trivial point that everybody should understand immediately, and that is that we're trying to choose between two options. We want to choose the one that's cheaper, that has the lowest cost or the highest benefit. And as a utility, we want to consider costs broadly. We want to look not only at the cost of direct dollars in and out of the bank account of our utility, we want to look at all the costs that will be faced by us and by our stakeholders. So that includes things like outages to our customers, the reliability of the system. That includes environmental effects and possible safety effects. And of course, not all of these come in dollars, and so it's sometimes difficult to decide whether a dollar of spending is worth an incremental improvement in reliability, and that is the fundamental purpose of asset management, or one of the main objectives of asset managers. Another problem that you run into, though, with cable is that costs aren't just coming in discrete blocks; they come in streams. And so you may be interested in evaluating one program or one option for addressing, say, a particular run of underground cable. Maybe you want to replace it, and that would be the upper graph. Option A, replace immediately, in which case you have an upfront capital expenditure and then streams of maintenance and risk cost associated with that cable that will increase over time. That might be one option, and that has a net present value associated with it, which of course is dominated by that capital cost at the beginning. I realize I'm taking everybody back to their engineering economics, but hopefully these terms will resonate. Then you may have another option with underground cable, say to rejuvenate it, maybe inject the cable, for example, in which case your capital spending comes in two chunks, one immediately, followed by a stream of risk and maintenance, and then another capital intervention some point out in the future for replacement. And even though the total capital spending may be higher in this case because we have two lumps of capital that we're going to spend, because of the discounting effect, the net present value, the effect on our pocketbook today could be lower. And our intuition isn't necessarily very reliable about this. It's sometimes hard to tell whether a dollar today, how it relates to a dollar tomorrow. So the point is that we need to be explicit about our assumptions and actually do the math to figure out which one of these is the better option. The other takeaway here that I think is really important to bear in mind as an asset manager is that spending money is costly and holding on to it is valuable, and we should be jealous about where we spend money on behalf of our ratepayers. Okay, so let's talk about the fundamental question when we're looking at cable. This is something that asset managers face all the time, and that question is, when should I replace an aging asset? So I've got a bunch of stuff that I installed out there in my system, and it's getting older, and I know that eventually it's going to have to be replaced. The question is when. And there's a conventional approach that most utilities use. This is where they start, and that's a technical approach. They'll say something like, well, when we installed this asset, this underground cable or this transformer or whatever it is, when we installed it, we thought it was going to last 35 or 40 years, and it's beginning to reach that age. So it's time for us to start thinking about replacing it. And the trouble with this is that this technical approach doesn't consider risk in any quantitative way. Like I say, it's a technical argument and it's a qualitative argument. And the other problem is when you sit down and ask yourself, well, what exactly did I mean by the useful life of this asset when I said it was 30 or 35 or 40 years? So every asset, whether it's an underground cable or a light bulb, is going to have a survival curve that's shaped something like this, that defines the fraction of the population that will remain in service as a function of the age. So for example, when the assets are 0 years old, right after we first put them into service, 100% of the population will be in service. And over time, as the assets fail, the percent remaining in service will decline. So this could apply to anything. The question will just be how steep is the drop-off and when does the drop-off start. That'll depend on exactly what kind of asset we're talking about. But if we say, okay, there's a curve like this for underground cable, and now let's look at it and ask ourselves, what's the useful life? And you could make an argument that the useful life is the median life, where half the population would still be in service, or that it's the mean life, which is a function of the area under the curve, or that it's the knee of the curve when the failure rate starts to increase, or that it's some target failure rate, maybe based on a reliability standard or something like that. And if you had a fifth engineer in the room, you'd have at least 5 opinions about what the useful life of the asset is. And the point here, the takeaway, is that the life of an asset is not a technical concept. It's an economic concept. And you should replace assets or refurbish them when the cost to do so is lower than the cost of continuing to operate them. So this is really how I believe that is the correct way to look at this question about when to intervene, either to replace or to refurbish, or whether to leave assets in place. And that's to recognize this, that when you're trying to make a decision about replacing an asset, you have two competing incentives that you're trying to balance. On the one hand, you'd like to postpone the year of intervention as long as possible in order to minimize your capital spending. You'd like to keep your money in the bank, or you'd like to spend it on other projects and delay the day when you have to actually replace your aging asset as long as you can. So that's one incentive, our downward sloping capital spending curve, our capital cost curve. On the other hand, the longer you leave an asset in place, the worse its condition will be, the older it'll be, and the more likely it is to fail. And so the risk will increase as we delay intervention. So in general, there will be this U-shaped total cost curve, the life cycle cost curve, with a minimum point out there somewhere. And that minimum point says, if you replace this asset on this schedule, you'll minimize the life cycle cost of ownership. And again, we're talking about a broad definition of cost, not just dollars in and out, but reliability and safety and all the other things that matter to us as a utility and to our ratepayers. Another important takeaway here is that it's asset specific. you can't say, based on an analysis like this, that underground cables have an economic life of 42 years. All you can say is that this particular cable run that serves these customers in this location, this one has a life of 42 years. But that one over there, that might be the same type of cable installed at the same time, in the same condition, but serves a different set of customers with a lower criticality. That one has a lower risk. If it fails, the consequences aren't as high, and that means it will have a longer economic life. So it's different for every asset. Okay, let's think about what information we need to have on hand in order to do that calculation that we were just looking at. I need to know about the replacement cost or the cost of intervention for the asset, and that's the capital spending. And I think most utilities know that kind of information without too much effort, so I'm not going to dwell on it. But the other thing that we need to know is risk, and we need to know how risk changes over time. So that means we need some estimate of the failure probability of the asset. Generally speaking, that means for underground cable, fitting some kind of a failure probability curve over our historical failure data. And what you're looking at here is an example of this that was done for a utility in the Northwest that had actually a pretty good database of failure history for their underground cable system. And you can see the failure rates versus age, the dots there, and then the fitted curve. And this curve was used for projecting failure probability and of course, risk for this utility. And then there are multipliers that were used as well to differentiate among different insulation types, different sizes of cable, and specific things that might be known about a particular cable run. For example, if a cable has had faults in the past, the perception is that increases the likelihood it'll have faults in the future. And so you can see in this table here that if a cable has had past faults, a multiplier of 2.0 is applied to the projected failure probability. So this is an example of how failure probability can be assessed. Now, a lot of utilities don't have this kind of data. Either their system isn't large enough or they haven't tracked it well enough to do a curve fit like this. And what that means is that either they can try to share data with other utilities or find some other source for industry information, of which there is some, not a lot. Or another approach that's very commonly used is to rely on a combination of subject matter expertise and whatever data is available to calibrate a failure probability curve that at least will be projecting the right total number of failures to match what they've seen maybe over the last couple of years. So I don't want to give you the impression that a very detailed, rigorous database is required to do this kind of thing, at least to get started. You can almost always make do with whatever you have, even if all you have is the opinion of the subject matter experts at your utility. Okay, so we know about probability of failure, and the other blade of the risk scissors, the other thing we need to know about is the consequence of failure. So this, what I'm showing you here, is a cartoon to give you the idea of what we mean by consequence of failure. Of course, there's going to be some direct cost to go out and replace or repair a failed cable, but the bigger deal, the thing that most people are really worried about, is that there are customers who will be out of service. And this is really what we're trying to avoid when we go out and proactively replace cables. So we'd like to have an idea of what is the cost of this event if it were to happen. So let's imagine we've got this feeder with some residential customers and an industrial customer attached to it. In a perfect world, we'd like to go knock on the door and ask these customers, well, there's a chance this cable is going to fail, and you'll be out of service for maybe 2 hours until we can switch you back in. How much would you be willing to pay us to avoid this outage? And then we'll use that money to refurbish the cable system. And so maybe your industrial customer would offer to pay $100, and the residential customers would offer to pay $5 each, and you could use that money to refurbish the cable. Well, of course, there's two problems with this. You'd never be able to collect the money from these ratepayers. And actually, you know, if you think about it, if somebody knocked on your door and asked you how much would you pay to avoid an outage, it's very difficult to come up with an answer. And that means that we're not going to know it based on actually asking the customers. We're going to have to infer or estimate the consequences of an outage in some other way. So there are various sources of information that utilities turn to estimate customer outage costs. I want to just emphasize a couple of them. One is that the Department of Energy performed a nationwide in the U.S. study, a survey of utility customers, electric customers, and has consolidated them online at a website called icecalculator.com. And if you go there, you can use that to figure out what their survey results were for how your customers would value an outage. Some utilities have done their own surveys. You see here a screenshot of a customer survey that Pacific Gas and Electric does every couple of years to try to estimate outage costs for their customers specifically. And then many utilities have a corporate risk matrix of one kind or another that gives them a way of estimating what is the risk posed by changing reliability or large-scale outages to their system. And sometimes those can be used to kind of back out what is the exchange rate between, say, dropping a feeder with 1,000 residential customers and a $1 million cost. In other words, how many points is one worth and how many points is the other worth? And that gives a way of inferring how your own specific utility values customer reliability. For most utilities that are starting out, especially smaller utilities that maybe don't have a lot of sophisticated, corporate planning methodologies at their disposal, or maybe don't have a risk matrix, I really would recommend the Department of Energy survey as a good place to start. It almost certainly wouldn't be challenged if you used that. Okay, so now let's talk about assessing consequences of failure. And we'll just look at a couple of scenarios here. One where we've got a tap. This is an underground cable tap that we're looking at here, and those numbers represent customers along the way. Five customers served by each transformer along the way as we move out along our tap. And then you see there's a switch out there where the tap can be looped if there's a fault. Well, if there's a fault in this feeder, the consequence is going to be first that all the customers on this, I said feeder, but I meant the tap. If there's a fault on this tap, the first thing that happens is that all the customers on here will lose power for a couple of hours until you can do switching, and then virtually all of them will be restored. So we can take that scenario, that number of customers, and our assumed duration for switching. Maybe we think it's going to take 2 hours, and we can calculate the cost of that using the assumptions from one of those customer surveys that we talked about before. Another scenario would be if we had a radial tap, and that's the one down below. And in this scenario, the cost would be a little bit different because instead of the customers being out of service for all of them for 2 hours, some of them would be out of service for much longer until we could actually get the fault repaired. So we'd be calculating, even though it's the same number of customers, the duration of the outage could be much longer, and so the cost would be higher. And what that means is that cables in radial taps are more critical. The consequences of their failure is higher, and they will have a shorter economic life than cables that are in a looped tap. Okay, so now we have the two things that we need in order to calculate risk. We have estimates of customer outage cost, and the intent here is not for you to memorize the table or anything like that, just to show you what they oftentimes look like. There will be some measure of dollars for both the SAIDI and the SAFE effect of an outage on residential, commercial, and industrial customers. And there'll be some number of dollars associated. Maybe it'll be per customer, or maybe it'll be per kilowatt for their average load. But a standard set of assumptions that you'll use for quantifying the cost of customer outages. And then we multiply that by the number of customers and the duration that we expect them to be out for failure of any particular cable segment that we might be interested in. And for each cable, we know how likely it is to fail if we know how long it is and how old it is. And we know the customer effects because we know which customers are served by each cable. And so that means we can calculate a risk matrix. And I bet that just about everybody who's listening here has seen one of these at one time or another. We're looking at here a real example from a utility, again, another one that happens to be in the Northwest. And what this plots is every cable segment in their system according to how likely it is to fail on the x-axis. In other words, how many faults do we expect there to be next year in each cable run versus the consequence of failure in terms of the customer effects. And so what this results in is an estimate that the total risk from the cable system is $26 million a year. And of course, it's rising because the probability of failure is increasing. And of that risk, only about $4 million is direct cost, meaning the cost to repair or replace failed cable. The rest of it is customer outage costs. And so hopefully that fits with your intuition that the customer effects are a much bigger deal to you if a cable fails than the direct cost to do the repair. So this should bring a question to your mind. You see this and you think, okay, I've got to make decisions about replacing cable. There's an obvious question that should come up, and that question is, so what? I know now what the risk is, but this doesn't tell me anything about what I should do about it. So I know that some cables are higher risk than others, but how do I decide which ones are actually worth replacing or injecting and which ones are not? And so that means we need to go back to our economic life calculation that we looked at the very beginning. So this is a slightly different form of it. That's looking at the trade-off between capital cost and risk cost, but it's the same basic idea. What we have here, the orange upward sloping curve, is the risk cost of an existing cable run increasing as the cable ages. It's getting more and more likely that it'll fail year by year and cause an outage to the customers. The blue dotted line is the levelized cost of a new cable. So you can kind of think of that like a cable mortgage. I'm going to install a new cable. I'm going to just kind of pay the interest and the maintenance costs going forward and spread it out over a large number of years so I can flatten it out. And so what I'm interested in is the point where these two curves cross, these two lines cross. So as long as I'm before the point where they cross, that means that the risk of the existing cable is lower than the cost of the new one, and I'm better off to leave it as is. On the other hand, once the curves cross, that means that from that point going forward, the existing asset, the existing cable is going to be more expensive than the new one would be, and I should replace it. So that means the point where those two curves cross, that's the optimal replacement timing for this cable. So if we're looking at one right here, the current age is 20, where the diamond is, and it looks like the optimal replacement timing might be age 30 or 32, this cable would have 12 years of remaining economic life before it should be replaced. We have another option too, though, when it comes to underground cable. We don't only have to look at replacement. We could also refurbish it. We could inject it. And the effective injection depends a little bit what your assumptions are about what an injected cable looks like. But for sure, what happens is you've rehabilitated it and reduced the probability that it'll fail going forward for at least some number of years. So what we're looking at here on the right-hand side is an example of how you might look at the benefits of injection. You can see there that the dotted line, we've taken a notch out of the risk curve going forward. And what that means is that instead of this cable reaching its end of economic life at age 32, like it did before, now it's going to reach end of economic life at about, it looks like maybe close to age 50, where the dotted line crosses. So we basically bought ourselves another almost 20 years of life by injecting the cable. And so that shaded area there is the risk reduction, the benefit that we get from injecting. And the question is that reduction in risk higher or lower than the cost of injecting the cable? If the avoided risk is higher, then that's a good candidate for injection. Our benefits outweigh our costs. And so that in this way you can use the same model, the same basic conceptual approach for evaluating various life cycle alternatives, including replacement in kind or upgrade with a new standard, say in conduit or injection of the cable, and figure out which option is most cost effective for various parts of the system. Okay, what you're looking at now is a screenshot of an actual cable evaluation model used by a utility, and I just wanted to show you this to maybe make it seem a little more real that it is actually something you can do. This isn't just arm waving. What you're looking at here is an evaluation of a single cable segment, and you can see a graph very similar to the one that we were just looking at here. You see the red risk curve rising over time. You see our leveled replacement cost curve for the new cable segment. And then there's also this blue dotted kind of parabola shape that goes over the top, and what that's calculating is the net benefit of injection year by year. So what we're saying is we could, we have multiple options. We could replace this year, we could inject this year, we could do nothing this year. Or we could replace next year, or we could inject next year, or we could do nothing next year. And so this model is evaluating all of those opportunities and identifying which one is the most cost effective. In this case, because the net benefit of injection is positive at the current age, you can see the orange dot, and you can see that the parabola, the injection benefit little dotted curve up above there is positive. That means that injecting this year is the most cost-effective strategy. And so this is a cable that we would say it's reached the point where it's at its end of life, and the optimal strategy is to inject it. So we go back to our risk matrix, and we're looking now at the same population of underground cables. The blue ones are the cables that are not at end of life, and the red ones are the cables that are at end of life. And so you can see that, as you'd expect, the ones at end of life tend to be concentrated either in cables that are more likely to fail, so they're further to the right on the graph, or in cables that have a very high consequence of failure. In other words, the ones that tend to be higher up on the graph. So the further you move up or to the right, the more likely it is that any particular cable is going to be at end of life. But there are surprises. You can see that there are bits of blue scattered in there among the red. In other words, cables that might be lower risk are at end of life even compared to cables that are higher risk. And the reason for that is that it doesn't cost the same to replace every cable. Some cables might be high risk because they're very long. And so the fact that it's long means that it's costly to replace it or costly to inject it. So that means that the benefit-cost ratio, the return on investment for that replacement program is not as high as some other cable. So there are some surprises. If you remember, when we looked at this risk matrix last time, the total risk was about $26 million. And it turns out that about 5% of the population is at end of life in this example. It means that they're currently due for replacement. Now the red blob here looks like a lot more than 5% of the cable segments, but that's because this is a logarithmic plot, and so they're really concentrated down at the bottom. You'll have to just take my word for it that really is only 5% of the population. That 5% is completely concentrated in high criticality cables in this case. So there was a real strong focus on commercial and industrial customers and on the larger cables that were part of the getaways from the substations or the trunk. In other words, places where the consequences of failure would be very high. That's where the program was most active. And there was virtually no spending on modern cable, only on the older HMWPE and XLPE cables where injection is really expected to do the most good, or replacement is really expected to provide the most benefit. Okay, so we've evaluated the entire cable program. We know which ones are at end of life now, and we can also know which ones are going to come due for replacement in the future. So this graph is from the same analysis. I'm just using this one for all the examples here, but what it shows is a large spike of spending. This is the capital program, a large spike of spending in the first year, followed by a fairly flat program going forward. So these bars, the dark blue represents the replacement program, the green represents an injection program, and the red is the reactive spending for future failures, for repairs and replacements of future failed cables. This is a very typical spending program shape where there's a spike up front, followed by, like I say, a flatter program going forward. In this case, there was about $37 million of near-term spending identified, of which about $7 million is injection and the rest replacement. But of course, because injection is so much less expensive than replacement, I forget what the ratio is, probably 5 to 1 or even higher. It actually is more feet of cable that are injected than replaced in this example. That near-term program reduced the total risk from 28 million, which is what it currently is, to about 4 million, even though, this is, I thought, very interesting, even though the failure rate really hasn't changed all that much. So what this graph that just popped up here, the small one, a little hard to read, but what it shows is the predicted number of faults going forward, starting this year and looking at next year. So the red is if we did nothing and just continued to run the system to failure. And you can see the steady increase in projected failure rate. And the blue is what happens if we follow this optimal program. So it's a flatter forward projection of failure rates. But you can see in the next year, the failure rate doesn't change all that much, yet we eliminate almost all the risk from 28 million down to 4 million. And the reason is that we're focusing on those most critical cables where the consequences of failure would be very high. So it turns out that for this example here, the benefit-cost ratio of the near-term program is about 10 to 1. So it's an extremely cost-effective program, one that easily passes muster with executives or regulatory bodies because the benefit to customers is so high compared to the cost of the project. Why is there a spike? The reason there's a spike, and like I said before, it's a very common result in these kinds of analyses. The reason is that one of two things. Either the utility has been underspending up until now. They've built up a backlog of work that they should have done, either replacements that they haven't done or just delayed work. And so they've got to figure out now how to get caught back up, right? They've built up that backlog. And the other reason there might be a spike is that even if the utility has been proactively replacing or injecting cables, they may not have been identifying the right ones. They may not have been getting the best bang for their buck. And so they still have built up a backlog of cables that even though they've been spending $1 million or $2 or $3 million a year in the past replacing cable, they missed some of the ones that they should have done. So that can comprise a spike as well. A lot of of course, an actual cable program isn't going to go segment by segment and scattered over the system. You're going to combine cables to make sensible projects that a contractor can execute. And what this shows here is a GIS map of underground cables that are color-coded according to whether they're at end of life or not, along with some of the supporting appurtenances like pad mount transformers and some of the other equipment that serves the cable system, switches and elbows and so on, that have different colors according to whether they're end of life or not. And you can combine them together using a very similar risk-based methodology to ask the question, okay, my model tells me that I should go replace the cables in this subdivision immediately, but the pad mount transformers all have 10 or 20 or 30 years to go before they should be replaced. Should I do everything while I'm there, or should I plan on going back and doing the transformers? And what you can see in this example here is as we move to the right-hand graph, when you combine cables and their supporting assets together, they all turn one color. And what that means is that in this example, it was better to do one project and replace everything all at once, even though not everything was necessarily at end of life, in order to save mobilization costs or other inconveniences from having two spending projects. I just think this is a good example of how the outputs of an analysis of a single asset class can be used to support a larger program going forward. Okay, in most cases, what you'll need to do then is to make a business case to explain either to, the utility needs to explain either to itself or to its regulator why the spending that it wants to do is cost effective. And so that means taking the results of the cable analysis and putting them into some kind of a standardized business case. And usually that includes things like a summary of the project, a description of what work is to be done and the cost estimate, and then a qualitative discussion of the benefit. And then there'll be a section on valuation. So what are the reliability effects and the avoided outages that we anticipate from this? What is the benefit cost ratio? What might be the rate impacts, things like that. And then lastly, a cost of delay. And that's one of the real advantages of a quantitative analysis like this is you can answer the question, what happens if I don't do this work? What happens if I ask for the money to do it and you don't give it to me? And you can make a quantitative statement about what the increase in the risk would be associated with that. I want to make a note about data. I mentioned earlier that you may not have all the data to support the full detail of the analysis that I'm describing here. As an asset manager, you want your decisions to be as data-driven as you can. It's kind of one of the fundamental tenets of asset management, consistent, repeatable, defensible, data-driven decision-making, or whatever the motto is. The point about this cable evaluation approach is that it can make use of whatever data you have. So if you've got detailed failure history, an approach like this knows exactly what to do with it. You can make explicit use in a very rigorous quantitative way. You can make use of whatever customer information you may have. So that means the type of customers and what their perceived outage costs are. And it can also make use in a quantitative way, whatever subject matter expertise is available at your utility. You have a place, a slot to put everything that will immediately affect the final recommended program that comes out of it. But it's not necessarily the case that you're going to have all this. And so I just want to emphasize the point that at each step along the way, there are approximations that you may have to make up for the fact that you don't have all the data that you'd want. So I already mentioned some of the things that you might do. You can lean on your subject matter experts to say, listen, we don't necessarily have a good failure history to predict, to fit a failure curve for all of our underground cable. What do you believe the failure probability is, or what shape do you think this curve should have? And you can use those assumptions in the near term until you're able to collect data to support modeling in the future. And then you just want to tell yourself, well, I made this assumption based on subject matter expertise, but going forward I want to collect the data to support a more rigorous analysis. And the point is, you're on the hook to make these decisions one way or the other. And so as an asset manager, you have to make do with whatever you have available. You have to do the best you can. Not making a decision isn't one of the options that's available to you. You can't wait around to have perfect data. So what have been the results of this? And I guess the real test of an analysis like this is how does it work in front of regulators and executives? So we have quite a bit of experience with this, and I just wanted to highlight a few of them. One of the common applications is really internal use by a utility. They're trying to ask themselves the question, how much cable should I replace or inject, or what should my programs be going forward? And they're using an analysis like this for their own internal purposes to plan their programs. And so who they're trying to convince are their asset managers and their executives and maybe their own internal board. So we've had very good success applying this methodology in that context. We've also had some specific experience with regulators, particularly in Canada, where the Ontario Energy Board is a very proactive regulator of the electric utilities that they regulate. And one of the clients that we've worked with, Toronto Hydro, developed what they call their feeder investment model, which applies this methodology for all of their asset classes, including underground cable. So the approach has been used in multiple rate cases by Toronto Hydro with the OEB, and the OEB has kind of singled out their FIM, in other words, this methodology for praise as being a very transparent and rigorous way to justify capital spending for aging infrastructure. So based on that, we believe that it's a credible approach for use with regulators. We're seeing now many of the other utilities, based on this, because of this result, we're seeing a lot of the other utilities in Ontario who are also regulated by the OEB picking up the methodology for their uses. And of course, they're not all as big as Toronto Hydro and can't afford the level of detail and don't necessarily have the data to support the level of detail that Toronto Hydro can. And so, as I mentioned before, they're having to make approximations and assumptions to fill in gaps in their data. And it seems to be working just fine. And then lastly, the CPUC, the California Public Utilities Commission, is currently drafting, or maybe they're circulating now, an internal memo to investigate whether they're going to recommend this approach to their subject utilities. So they've looked at it and seen enough value in it that they believe it's worth considering. That's the end of my presentation. I again appreciate your time, and I see that some questions have come in, and we will try to answer them.
Thank you, Darren. Yes, we have received some questions from our audience, and the first one we will ask is, what is your view on testing?
So testing fits in pretty well in this kind of an analysis. You can do a cost-benefit evaluation of testing by asking yourself, if I knew this cable was in bad condition, how would that change my my decision about whether to replace it or inject it, for example. And so you can kind of treat cable testing as an intervention to be evaluated, and treat the benefit of testing as the information that you get, the reduced uncertainty that you'd have, after the test was completed. What we have seen is that a couple of things. One is that testing is expensive, and so it's not justified necessarily all the way across your system, just carte blanche. You wouldn't really test every single cable. But there are cases where two things are true, where the cable is very critical and where the results of the test might change your spending plan, where it can be beneficial.
Thank you. We have another question. What about the initial capital cost to install the now old cable?
Okay, that's a really good question. From an economic perspective, the capital cost to initially install the cable is what's called a sunk cost. So you install the cable in 1972, and now you're trying here in 2016, trying to make a decision about whether to replace it. Well, that initial capital cost is gone, and there's nothing you can do to get it back. And so it's technically not relevant for decision making going forward. So we ignore it.
Thank you. And what is the cost of injection compared to new cable? Does it depend at all on insulation wall thickness?
Maybe this would be a good one for one of the Novinium people who are listening in to chime in on. I can tell you what the utilities that I've worked with have assumed, and that is that, no, they have not assumed that there's going to be a difference in injection costs with wall thickness. And the ratio depended a lot on what their installation practices were, but at least 5 to 1, I would say, has been my experience. I heard somebody else come in. Go ahead.
Darren, it's Wade here, and yes, mostly it's somewhere between 20 and 40% of the cost of replacement, and it's the insulation wall thickness, depending on voltage, cable size. Will mean that the prices are different, but the same as a 1/0 is a different price than a 500 MCM cable. The larger cable has more fluid to inject in it, might take a little longer, but the cost differentials are still substantial. So we generally see anywhere from 20 cents on the dollar to 40 cents on the dollar in terms of replacement cost.
Okay, thank you. And our next question, is injection the only way to eliminate partial discharge in cables?
I think that's a technical one for you guys again, Wade. I don't know if you want to weigh in on that. It's not something that I have.
I'll give it a shot. Not being an expert, but depending on the level, if the injection process addresses water trees, and water trees have been shown to create electrical trees and most of the cable failures. And when we look at our failure history from injection, we've injected millions and millions and millions of feet of cable, 200 utilities around the country. The failure rates are comparable to newly replaced cable. So what we see on significant PD though is that there's a line where if it's so significant that it needs to be replaced because the process for rejuvenation just can't address it. So when PD becomes electrical trees, we don't recommend rejuvenation. We generally see about 75% of all cables that we address that are able to be injected, and then 25% aren't due to either neutral issues or massive PD, and then we tee them up for replacement.
Thank you. And then our next question, can all cables be injected? Do you have to replace elbows and splices?
Do you want me to take that one?
Yeah, go ahead.
So I think I'd answer the first part. It's a horses for courses. Every utility is different, and every subdivision and every utility is different. We've experienced every kind of situation there is. If you're interested in us coming and meeting with you and introducing you to some other utilities nearby that have experienced rejuvenation and have a chat with them as well. Will help a lot in terms of understanding what's involved. But we recommend replacing elbows. There is a way to do a process with what we call injection adapters. But as a rule, since we're de-energizing cables at least partially to do the injection process, we generally recommend replacing the elbows and as well as some splices. We have a process that is a low pressure IUPR process that often flows through splices, and we'll do that in many instances. We'll replace the elbows and we'll re-energize the cables, and we can inject over-energized cables and through splices. And sometimes the splices, depending on the splice type, pin and socket or taped or something, they're not able to be injected through. So at that point, we would recommend digging the splice, repairing the splice with a brand new splice, and then we can inject through that. There's a line where we would maybe not inject a segment with many splices, but as a rule, we have many customers that we have a very comprehensive program of repairing splices and reintroducing the cable with new splices, new elbows, and a 20 to 40 year warranty.
From a cost-benefit perspective, my experience has been that the fact that the elbows are replaced has been a real benefit because they can be such a significant source of failures. Just toss that in.
Thank you. And our next question, how does injection costs compare to other cable repair methods or identifying PD locations?
Wade, I think you might be on again.
Okay. Cable repair methods are identified. So testing for identifying partial discharge, there's different ways to do it, and when we do our assessments and we do our TDR to determine the quality of the cable and its ability to be injected, we do some forms of PD testing. As a rule, I think I'll throw it back a little bit to Darren. I'm not an expert in testing per se in terms of costs. What I've heard is that the costing for mostly the PD is offline. That means you have to de-energize and you thump the cable and you put a high bunch over voltage through it, and it creates a lot of strain on the cables and it creates its own problems. Injection is a low. It's low invasion or not very invasive. It doesn't really impact the cables or hurt the cables. And when we're looking at them, we make an assessment of which cables are in really bad condition. And the ones that are in bad condition and that have high PD, as a rule, we're not going to inject anyway. The ones so those ones would be left for later replacement or additional testing, what you like. But the injection costs are comparable to testing, a little bit more, but the beauty of the injection is you get your 20 to 40 year warranty and you get cable back to near new condition. Whereas with testing, you leave the cable in the same condition you found it and you haven't significantly upgraded it. So Darren, got anything to add to that?
Yeah, I would just add that the cases where you do have to take an outage to test, it's a bit hard to make the case that that's worthwhile because what you're trying to avoid is the outage. You know, the reason you're interested in testing cables is to find the ones that are likely to fail. So you're taking an outage to avoid an outage, which is a bit of a difficult case to make. So I think my tentative opinion, I guess, about testing is that it can be cost effective in certain cases, but I don't necessarily see an application for it across the board.
All right, thank you. I think we have time for one more question. Darren, would you like to choose the last one?
Well, I don't see what they are, so I'm not going to be able to do that.
Okay. I'll ask one more then. We have engineers who have strong opinions about cable, when they fail, what to do about it, etc. How do you work with these guys?
So this is a pretty common situation. Utilities will have experienced people who, based on their experience, will develop strong opinions about what ought to be done with the underground cable. Whether, sometimes they'll have opinions that you should never inject it, or that it all must be replaced and brought up to current standards, installed in conduit, or whatever it is. And one of the real benefits that we've seen of using the economic life approach that we just talked about is that it kind of brings them inside the tent a little bit, because you're leaning so heavily on subject matter expertise in order to define what the input assumptions are going to be, the failure rates and the consequences of failure and so forth, that you get a chance for those people to be heard, but not necessarily to drive what the final program is going to be. So you're asking them for their subjective expertise in areas where they really are experts, like what happens when a cable fails, or what's the difference between a cable that's installed in conduit or direct buried, or what are the effects of degraded neutral. That is where their expertise is strong. And you're not leaning on them in areas where their expertise may not be as strong, such as how much money should we spend injecting underground cable next year. That isn't. I don't mean this as a slam on them in any way, but that's beyond their expertise. It's not something that, by virtue of their job, that they're necessarily in a position to address. So I guess I would say that one of the real benefits of this approach is it kind of gets everybody to put their cards out on the table, and it really helps to keep everybody on side.
All right. Thank you so much, Darren. For anyone with questions still unanswered, we will be able to get in touch with you one-on-one. And Darren, we thank you for taking the time to speak with us today, and thanks to everyone for joining us. We hope you enjoyed the webinar and look forward to our next Masters of Reliability webinar with Tom Brule of St. Charles Municipal Electric Utility on February 24th. Thank you.
Thanks, everybody.